Hello everybody. Now we shall discuss about DC potentiometers. A potentiometer is an instrument designed designed to measure an unknown voltage by comparing it with a known voltage. A potentiometer is an instrument designed to measure an unknown voltage by comparing it with a known voltage. Okay, so this is an instrument for the measurement of unknown voltage with the help of known voltage. Okay, this known voltage may be supplied by a standard cell or any other reference voltage source. Okay, this could be standard cell. This will be supplied by a standard cell or any other reference voltage source. Now let us discuss about the operation of basic slide wire potentiometer. Basic slide wire potentiometer. Let me draw the circuit diagram of a basic slide wire potentiometer. This is variable rheostat. This is battery. Let this is EW, working voltage. This is unknown EMF, unknown voltage, and this is standard cell. This is known reference voltage, standard cell. You're going to have sliding contact, sliding contact. Galvanometer. This is slide contact. This is key. And this is galvanometer. And this is operate position. Operate. Let this is calibrate position. Calibrate position. Okay, now when this is switch, right? A switch S. Okay. When the switch is when the switch is thrown to operate position, and the key is opened, and the key is opened, then this is not connected to this circuit. Okay. Now here see, this is slide wire. Okay, this is slide wire. Along with this slide wire, you're going to have scale. Okay, so 0, you're going to have scale. The length of this slide wire is 200 centimeters, and here 1 centimeter length of this slide wire will be having the resistance of 1 ohm. The resistance of 1 centimeter slide wire is 1 ohm, means 200 centimeters means 200 ohms. 200 centimeters is 200 ohms. Okay, so it is having the resistance of 200 ohms, because this slide wire is designed in such a way that the 1 centimeter in such a way that the 1 centimeter of length of slide wire is equal to 1 ohm resistance. Okay, so the total length of slide wire is, as total length of slide wire is 200 centimeters, the resistance will be 200 ohms. Okay, now when the switch is thrown to operate position, okay, the switch is thrown to operate position, and the key is opened, and the key K is opened. Okay, then you're going to have this circuit only. You're going to have this circuit only, right? Okay, now the current which is flowing through this circuit is working current. Okay, this is called working current working current. Okay, so working current IW is equal to EW by RH plus resistance of slide wire, that is 200 ohms. Okay, when the switch is thrown to operate position and the key is opened, then you're going to have this circuit. Okay, then the current which is flowing through this circuit is working current IW. Okay, now okay, here what is the process of finding this unknown voltage? Okay, now here uh, when the switch is thrown, when the switch is thrown to operate position, operate position and the key is closed, and the key is closed, and the key is closed. Okay, so you close this key. Okay, okay, so when the switch is thrown to sorry, okay, now when the switch is thrown to operate position and the key is closed, and the key is closed. So now the key is closed now. Okay, then this galvanometer gives some deflection. If it is giving deflection means the voltage across this portion will not be equal to this voltage. Okay, voltage across this portion is not equal to voltage of this unknown EMF. Okay, then what we do is you change the position of the sliding contact until galvanometer shows null deflection. Okay, so change the position of sliding contact until galvanometer galvanometer gives null deflection. Okay, so change the position of sliding contact until galvanometer shows null deflection. Okay, so now you change the position of this sliding contact. Okay, let this is the position of sliding contact let this is the position of the sliding contact at which balance condition is obtained. Okay, let this is A, let this is point C. Let this is the position of sliding contact at which the balance condition is obtained. Okay, actually you have to change the position of the sliding contact. Okay, let this is the position of sliding contact. Earlier, let this is the position of the sliding contact. Now you change the position of the sliding contact until this galvanometer shows null deflection. Okay, now you place the sliding contact at this position. After placing the sliding contact at this position, suppose if it is showing null deflection means voltage across this portion will be equal to voltage across this. Okay, so let this is the position of sliding contact at which galvanometer shows null deflection. Okay, then voltage across this portion, let EAC is the voltage across this portion. Okay, then EAC will be equal to unknown EMF. Let E is the unknown EMF. Okay, what will be this EAC? Working current into resistance across this portion of the sliding contact. Okay, RAC. Okay, let this is 100 centimeters. 100 centimeters length of sliding wire will be having the resistance of 100 ohms. Then this will be equal to IW into 100 ohms. Okay, so we should know the value of this working current. Okay, before going to find this unknown EMF, let us go for standardization. We will go for standardization. Okay, what is standardization? Okay, standardization. What is mean by standardization? Okay. Now here what we do is the switch is thrown to the switch is thrown to calibrate position. Calibrate position. Calibrate position, and the key is closed. Key is closed. Okay. So the key is closed. The switch is thrown to calibrate position. Okay. The switch is thrown to calibrate position. Okay. Normally, the voltage of the standstill is 1.0186 volts. 1.0186 volts. Okay. Now here, anyhow, the switch is thrown to calibrate position and the key is closed. Okay. Then some current will be flowing to this galvanometer. It gives some deflection. Okay. Now what we do is you change the position of the sliding contact until it gives zero deflection. Then voltage across this portion will be equal to voltage across this. But instead of doing like that, what I am going to do is I am going to place this sliding contact at 101.86 centimeter mark on sliding wire scale. I am going to place this sliding contact at 101.86 centimeter mark on the sliding wire scale for the sake of convenience. For the sake of convenience, I am placing the sliding wire contact, sliding contact at 101.86 centimeters mark on the sliding wire scale. Okay. Now this is placed at this scale mark. So that is 101.86 centimeters. Now the length of this slide wire from here to here is 101.86 centimeters. Okay. Then the resistance from here to here will be 101.86 ohms. 86 ohms. Let it give some deflection. Let this galvanometer give some deflection. Okay. Now what we do is vary RH until galvanometer gives null deflection. Vary this RH until galvanometer gives null deflection. So you adjust the value of RH until galvanometer shows null deflection. Now we have changed this RH until this shows null deflection. Balance condition is obtained. Okay. After varying RH, null condition is obtained or balance condition is obtained. Now it is showing null deflection. After weighing this RH, now it is showing null deflection. If it is showing null deflection means what will be the voltage across this portion of the slide wire? Nothing but the voltage of standard cell, that is 1.0186 volts. So the voltage across this will be equal to voltage across this. When there is no potential difference between these 2 points, then no current will be flowing to this. When no current is flowing to this galvanometer means voltage across this portion from here to here will be equal to voltage across this standard cell. Okay, now you can find anyhow no current is flowing to this, means voltage across this is 1.0186 volts. Anyhow, you know the value of resistance across the portion of this sliding side wire. So you can find the value of working current, that is IW is equal to 1.0186 volts by 101.86 101.86 ohms. 101.86 centimeters, nothing but 101.86 ohms. Then you're going to get 10 milliamps. Now the potentiometer has been calibrated. Once this calibration has been done, then this will get unchanged. Okay, now the working current is 10 milliamps. That's it. Okay. Now we do one thing. After the completion of calibration, okay, uh, let me write the definition of standardization. What is standardization? The process of adjusting the working current so as to match the voltage drop across a portion of of sliding wire against a standard reference voltage is called as standardization. Okay. So it is the process of adjusting the working current so as to match the voltage drop across a portion of sliding wire against a standard reference voltage. Okay, see here. You are changing RH. Okay, so it is the process of standardization is the process of adjusting working current. How can you adjust this working current? By varying RH. Okay, it is the process of adjusting the value of working current so as to match the voltage drop across a portion of sliding wire. Okay, this is the process of adjusting this working current so as to match the voltage drop across this portion of sliding wire against a voltage standstill voltage. against a standstill voltage is called standardization. Okay, it is a process of adjusting working current in order to make these two voltages equal. That is voltage across portion of sliding wire and voltage across this standard cell. That is called standardization. Okay. Now what we do is, anyhow this is standard cell. Okay. Now finding unknown voltage. How can you find unknown voltage? Standardization has been done. Now the working current is 10 milliamps. Okay, the current which is flowing through this is 10 milliamps. Okay, 10 milliamps, right? Okay. Now the switch is thrown to operate position. The switch is thrown to operate position and the key is closed. And the key is closed. Okay. Finding this unknown EMF. Okay. Now what we do is change the position of sliding contact until galvanometer gives galvanometer gives null deflection. Okay. So you change the position of this sliding contact. Okay, until this galvanometer gives null deflection. Okay. Let this is the position of sliding contact. Earlier, let this is the position of sliding contact. It has been changed from here to here now. Okay. So let me change the position of this sliding contact until this galvanometer gives null deflection. Okay. So after changing the position of this sliding contact, if it is showing null deflection, means voltage across this will be equal to voltage across this. Voltage across this portion of sliding wire is equal to voltage across this unknown EMF. Okay, anyhow you know the value of current which is flowing to this, that is working current is equal to 10 milliamps under balanced conditions, under null conditions, under balanced conditions. Okay, the current which is flowing to this will be equal to 10 milliamps. Okay, now let this is the position of sliding contact. Let this is 150, or you do one thing, sorry, okay, 156.8 centimeters mark. Okay, after placing the sliding contact at 156.8 centimeter mark on the sliding wire scale, the balance condition is obtained. Let us consider like this. Let it gives null deflection when it is placed at this mark 156.8 centimeters. This mark is 156.8 centimeters. Okay. Then what will be the voltage of unknown EMF? Okay, you know the current which is flowing to this is, let this is point A and this is point C. Okay, that EAC is nothing but unknown EMF E, which is equal to simply IW into RAC. IW is 10 milliamps. What is RAC? RAC is nothing but 156.8 ohms, okay, which is equal to 1.568 volts. So the unknown voltage can be determined like this. Okay, so unknown voltage can be determined. So in order to find unknown voltage, first we go for standardization. Then after, uh, uh, by doing standardization, we can find this working current. After finding working current, okay, we will come to know the value of unknown voltage. Okay, by changing the position of sliding contact. If it is showing null reflection, by changing the position of the sliding contact means voltage across this portion will be equal to voltage across this. Okay, this unknown EMF is nothing but voltage across this portion. Okay, likewise you can find unknown voltage. Okay, so a potentiometer is an instrument designed to measure an unknown voltage by it comparing it with a known voltage standard cell. Okay, now coming to the advantages, a high degree of accuracy can be achieved if we make measurements by using comparison methods. Okay, here we use comparison method. As we use comparison method over here, a high degree of accuracy can be achieved. This is one of the advantages. Why we achieve high degree of accuracy by using comparison methods? Because the quantity to be measured, that is unknown voltage, the quantity to be measured doesn't depend upon the deflection of the pointer. Like in case of indicating instruments, quantity to be measured is depending upon the deflection of the pointer. But whereas in case of potentiometer, the quantity to be measured is not depending upon the deflection of the pointer, but depends upon the reference voltage, source. That's why if we make measurements by using comparison methods, high degree of accuracy can be achieved. So this is very accurate method. Finding unknown voltage using potentiometer is very accurate method, as we have chosen comparison method. Okay, so this unknown, the quantity to be measured is not depending upon the deflection of the pointer, it depends upon the known voltage. Okay, this is one of the advantages. Coming to another advantage of the potentiometer is that since a potentiometer makes use of balance or null condition, it makes use of balance or null condition. Since it makes use of balance or null condition, no current flows through this unknown EMF. If the galvanometer is balanced means, if the galvanometer is giving null reflection means, no current will flow through this unknown EMF. When no current is flowing through this unknown EMF means, there will be no power consumption in the circuit containing unknown EMF. No power consumption in the circuit containing unknown EMF. Unknown EMF when the instrument is balanced. When the potentiometer is operated under balanced conditions, no power consumption will be there in the circuit containing unknown EMF. Okay, so when the instrument is balanced, when this galvanometer is showing null reflection means no current will be flowing to this. When no current is flowing to this means there will be no power consumption in the circuit containing unknown EMF. So the determination of voltage by a potentiometer is independent of source resistance. Independent of source resistance. Okay. This potentiometer normally the potentiometer is extensively mostly used for a calibration of voltmeters and ammeters. This potentiometer is treated as ideal voltmeter. This can be treated as ideal voltmeter as this potentiometer makes use of balance condition or null condition. This can be treated as ideal voltmeter. Almost it is nearly equal to ideal voltmeter. Okay, that's why this is mostly used for a calibration of voltmeters and ammeters. Okay, this is also used for a calibration of voltmeters and ammeters. The potentiometer is extensively used for a calibration of voltmeters and ammeters. Thank you.